Module 5, Investigation 2, Concavity and Average Rate of Change. At 5 p.m., Karen started walking from the grocery store back to her house. Fill in the below table by determining the number of feet Karen is from home, D. Then use the information in the table to determine the average rate of change of the number of feet Karen is from home with respect to time, measured in minutes since Karen started walking on the specified interval. So I drew a quick sketch of the situation. Here's the grocery store, here's Karen walking to her home from the grocery store, and then D is the number of feet Karen is from home. So we have the number of minutes since Karen started walking. In this column we have all of those. Then we have the number of feet Karen is from home. So you change in number of minutes since Karen started walking. This will be the easiest one to fill out. The change in time delta t is just the final value minus the initial value. 0.5 minus 0 is 0.5. 1 minus 0.5 is 0.5. All of these changes are 0.5. The number of feet Karen is from home, D. How are we going to figure that out? Let's see, we have the change in the number of feet Karen is from home is negative 1.5. So that means this final value minus this initial value is negative 1.5. So I decrease 1.5, and that means that I'm going to end up 116.5 feet away. Notice if I subtract 116.5 minus 118, we get negative 1.5. So I just calculated that by 118 minus 116.5. That's not what I did. I took away 1.5 and got 116.5. Okay, now the next one. I have 116.5, then I take away 3.2, I get 3.2 feet closer, and so I'm at 113.3. I should probably mention where this is coming from, just give it some symbolic foundation. We know that the final value minus the initial value equals the change. So that means that if we add initial to both sides, the final equals the change plus the initial, or the initial plus the change. And here, since our changes are all negative, adding a change is the same as subtracting, because we're adding a negative. So I just subtract each of these. Same thing here, 113.3. That's our initial value plus our change of negative 6.5 gives us 106.8. Then I can take that value, make it my initial, and add the change of negative 7.1, and I get 99.7. So I noticed that these changes in distance, they're actually decreasing because they're becoming more and more negative. But at the same time, she's getting, with each 0.5 second interval, she's covering more distance. So that negative is just because this distance is decreasing. Although she is getting closer to home, her speed is increasing. That's why this is getting greater, but the negative just signifies that this is shrinking here. Okay, average rate of change of Karen's distance with respect to time. Let's see. So we have the change in the number of feet Karen is from home, and the change in the number of minutes since she's been walking. That's all average rate of change is the change in the distance over the change in time. I'm just going to write that over here. So we just need negative 1.5 divided by 0.5 gives us negative 3. Then change in distance over change in time, negative 3.2 divided by 0.5. It's negative 6.4. Then the change in distance of negative 6.5 divided by 0.5 is negative 13. Then negative 7.1 divided by 0.5 is negative 14.2. So I notice here that the average rate of changes are also becoming more negative, not at a uniform rate. This one's kind of a big jump here of 3 units. This one's a bigger jump of almost 7 units. This one's only a jump of about 2 units. So there's something interesting going on with the average rate of change. Sketch a graph of the number of meters Karen is from home. So number of meters, we have feet. In terms of the number of minutes since Karen started walking. Okay. It's probably a typo, but I'm going to go ahead and convert. I don't want to convert all these feet measurements to meters. Let me see if I remember how to do that. Okay, so we know that in, let's see, 12, there's 1 foot, 12 inches in 1 foot. So if we multiply 99.7 feet by this factor, we're really just multiplying by 1 because these are equal. 12 inches is equal to 1 feet. Furthermore, we get our units to cancel out here. And then we move on. There's 2.54 centimeters in 1 inch. Now the inches will cancel out. Let's see. There are 100 centimeters in 1 meter, so our centimeters can cancel out. Notice now the only units that we have left are meters. Now I'm going to just multiply these numbers together to see what our conversion factor is. This is 99.7 times 0.3048. Which gives us 30.3886 meters. So 30.4 meters here. Let me just put this in red. And likewise, we can multiply each of these by that conversion factor, 0.3048. 106.8 times 0.3048 is 32.55. And we can do the same thing here. 113.3 times 0.30 and 116.5 times 0.3048. And we can convert all of these to meters. Okay, now we wanted to sketch a graph of the number of meters Karen is from home in terms of the number of minutes since Karen started walking. So I'm going to make a graph, and I just used the positive horizontal and positive vertical axis because all our time values and distance values are positive, and my number of minutes goes up. Let's say we have 1, 2, 3, 4, 5 values from 0 to 2, so I need to have my scale just go up by 0.5. So here on my program I can turn on some grid lines, and then I'm going to make 1 unit or 0.5 units, 1, 2, 3, 4, 5 of these little grids. So 1, 2, 3, 4. Okay, so that gives me my time values. Could have made that scale bigger. Okay, now if I'm going by meters, I need to fit in, let's see, all the really interesting stuff happens between 30 and 36. Okay, so for this vertical axis, what I'm going to do is just call the ground level 30, so that 30 meters is right here. And then I'm just going to go up by 5 again. And I just needed my range to be between 30 and 36, and so I had 4 tick marks here, so if I divide 36 by 6 by 4, I get 1.5, so I just went up by 1.5 each time. But now I'm ready to plot these. So when the time is 0, the number of feet from home is 35.97, 36. And let's see, when the time is 0.5, the number of feet from home is 35.5. I'm going to do a quick calculation here, because the difference between 36 and 34.5 is 1.5. And then I divided that up into 5 units, so each of these units, 1.5 divided by 5 is 0.3. So 35.5, well, if I'm at, let's see, 36, and I subtract 0.3, this will be at 35.7. If I subtract another 0.3, I'll be at 35.4, so my next dot needs to be somewhere about right here. Then after 1 second, I'm at 34.53, which is just a little bit above 34.5, but like up here will be 34.8. I can really not go much above there at all. Then at 1.5 I'm at 32.55. So 32.55. If I'm at 33 and I take away one of those small squares, I'm at 32.7. If I take another 0.3 away, I'm at 32.4. So I need to be in between here. I'm not taking away 2 whole squares, I'm not taking away just one, but maybe somewhere around here. Then the last point, 30.4, is pretty close to the bottom here. So we should have a graph that looks kind of like this. Hold on, let me see if I can get a curve to fit there. This isn't perfect, but something like this. Our next question, is the graph you drew above concave up, concave down, or some combination of both? This one is always concave down. You might remember hopefully I gave this to you, a packet. Important information from Module 5 from the online text. And there's a little box about concavity on the second page. And it says, when the rate of change of a function is increasing on an interval of the function's domain, we say the graph is concave up on that interval. And when the rate of change of a function is decreasing on an interval of the function's domain, we say that the graph is concave down on that interval. So let's look at our rate of change. Our rate of change is becoming more negative, so it's decreasing. You can look at this line. It's as the input increases, the output always decreases. The slope, the steepness, is getting smaller and smaller till we have a really negative slope around here. So this one is concave down because the rate of change of the function is decreasing on the interval of the function's domain. There were also a couple of charts on page 1 with like decreasing at a decreasing rate. That's what we're looking at here, concave down. When you get to calculus, your teachers will probably maybe like draw a picture like this and say if you have something like this, concave down, or if you have something like this, you're concave up. Ours is clearly concave down, like you're holding a bowl and it's falling upside down. But the key here is that our rate of change is decreasing. It's becoming more negative. Like if you drew a line at any of these points, let's say this point right here, if you drew a line that had the same slope as the function at that point, this is called a tangent line. And then if you drew like another tangent line over here at this point, which line has the most negative slope? It's this second one. For each of these successive points, the slope of the tangent line would decrease, and that tells us that it's concave down. And the slope of the tangent line is precisely the instantaneous rate of change, or the derivative. Part C. Oh, we just did that. Concave down. Concave down because the rate of change is decreasing over the interval 0 to 2. Describe how the quantities number of minutes since Karen started walking and the number of minutes Karen is from home change together. Looking at our blue graph here, as the number of minutes increases, the distance from home decreases. And we could look at that all sorts of different ways. We could look at it at the table as the number of minutes increases here, the number of feet from home decreases, and we could think about it with our picture as the more she walks, the smaller that distance will be. You could also look at the changes if you want to for each 0.5 minute increase. There's these corresponding changes, and notice the changes are also decreasing. So she's walking home faster and faster. That's because her rate at which she's walking home is becoming more and more. It's negative because we're moving toward home, but really she's getting faster and faster. That was a pretty cool problem, but we really needed to be precise with our graph or else it all falls apart. Number 2, you have finished your bath and pulled a plug from the drain. As the water is draining, you record the number of minutes N and the height of the water H in centimeters of the water in the tub since the plug was pulled. Fill in the below table by determining the change in the number of minutes delta N and the change in the height of water delta H over specified intervals. Then use this information to determine the average rate of change of the height with respect to time, measured in minutes since the plug was pulled on the specified intervals. So just looking here at the change in the number of minutes elapsed, we can find these by the final minus the initial. 1.5 minus 1 is 0.5. 2.6 minus 1.5 is 1.1. 4.5 minus 2.6 is 1.9. 7 minus 4.5 is 2.5. And it might be helpful to remember what I'm thinking about. Finished your bath and you pull the plug from the drain, so the water is draining out of the tub. So there's some changes in time, and then our height, of course, is decreasing, and we can find the change, final minus initial, 45.75 minus 50 is negative 4.25, so there's a decrease. Let's see, 37.83 minus 45.75 is negative 7.92. 29.83 minus 37.83 is negative 8. 20.83 minus 29.83 is negative 9. Okay, so we see that the change is becoming more negative, so we can say the changes are decreasing. That means that, what does that mean? All these changes in minutes are decreasing also, so I guess it makes sense that if we consider more time, more water will have drained, right? This is different from the last problem where all the changes were equal. But here I think that it makes sense that the water would drain at a constant rate, because only so much water can get down the drain. So I'm hypothesizing that the average rate of change will be constant here. Let's see. So the average rate of change of height with respect to number of minutes elapsed is just delta H over delta N. That with respect to tells us that we're going to divide by the delta N. This is different from with functions where it was sort of reversed from what you were thinking. Here it's exactly how we would write it. The change of height with respect to the number of minutes elapsed. So negative 4.25 divided by 0.5 is negative 8.5. Negative 7.92 divided by 1.1 that's negative 7.2, so right away I can see I was wrong in my guess that the rate of change would be a constant. Negative 8 divided by 1.9, negative 4.21. Negative 9 divided by 2.5 is negative 3.6. Okay, so it's not a constant rate of change, but what's happening here is the rate of change is becoming less negative, meaning that the rate of change is increasing. Okay, so sketch a graph of the height of the water in centimeters with respect to the number of minutes elapsed Since you pulled the plug from the drain, be sure to label your axes. So here are my axes. I got my height in centimeters on the vertical axis and the number of minutes on the horizontal axis. Notice that the number of minutes I have go from 1 to 7, so I'd really like this axis to go from 1 to 7. I counted up all these little grid marks up to about here, and I have about 34. So about right here would be 35. So I'm gonna just say 35 divided by 7 is 5, and so I need about each little unit to be 5 of these little grid marks are units. So 1, 2, 3, 4, 5. It'll be 1 minute, 2 minutes. Okay, there's my horizontal axis. Now my height in centimeters, good thing we have the same units here. I'm going from about 20 to 50. I'm just gonna, let's see, start my graph. Like I'm gonna have the origin here be the point 0, 20. So 20 is gonna be right at the bottom. And I've got to go all the way up to 50. I think that would be okay if we go up by units of 5 here. So just going to do the same 5 unit pattern. So this point here will be 25. Then I'll go up 5 more units and all the way up to 50. Okay, I didn't plan that out very well. It wasn't quite enough, so my 50 is way up here. Okay, let's graph this. When the number of minutes elapsed is 1, the height is 50. So when we're at 1 minute, the height is way up here at 50. When the height is 1.5 minutes, I'm sorry, when the number of minutes is 1.5, then the height is 45.75. So 1.5, that's 2.5 of these, so somewhere right there. I'm just going to mark that to remember. And then 45.75. Each of these tick marks is actually 1, 46, 47, 48, 49, 50. So 45.75 is just about 46. So I start at this point and go up 46, about right here. 2.637.83. Let's see, here's 2.5, so 2.6 would be about right here, and I want to go up to 37.83. Here's 35, 36, 37, 38, so somewhere about right here. 4.5 and 29.83. Okay, 7 and 20.83, so about 21. Okay, now let's see if we can connect the dots. Something like that. It's not perfect, but shaped like this. We should, since our rate of change is actually increasing, we should have concave up here. We should have, we start with a really negative slope. Like if we drew a tangent line, oops. Uh-oh. Okay, let me try this again. If I draw a tangent line at this point, so I want a line that sort of has the same slope as this function does at that point. something like that. Then, okay, so I got another graph. There's a tangent line, and then if we drew another tangent line, say for this point, you should see that this slope is more negative than this one, so the slopes are increasing. And you can see that here, the average rates of change increase, they become less negative, approaching 0. Same thing with these. And so that means that we have concave up when the rate of change of a function is increasing on an interval of the function's domain. We say the graph is concave up on that interval. So even though our function is decreasing, the rate of change is increasing. So that's the answer to this one. Is the graph you drew above concave up, concave down, or some combination of both? Definitely concave up, because the rate of change is increasing. And I've said it before, I'll say it again. Anytime you have this sort of shape, it's kind of what we have here. We have this little piece of it, a bowl pointing up, that's concave up. If we drew tangent lines all along here, the slopes of them would all be increasing as we move from left to right. Whereas something like this, the bowl pointing upside down, is concave down. The slope of the tangent line is always decreasing. The rate of change is always decreasing as the input increases. Part D. Use the table you created in Part A to explain how patterns in the average rate of change of height with respect to the number of minutes relate to the concavity of the graph. Describe why it is valuable to examine the average rate of change of the height with respect to the number of minutes elapsed on intervals of the domain. So basically, if the average rate of change is decreasing, then your graph is concave down. And if the average rate of change is increasing, the graph is concave up. And why is it valuable to look? Well, we could try to just look at the changes in height. Like here, the changes in height are all decreasing, and over here, the changes in height are also decreasing. But here we could see that we had a fixed change in time, and so really we could just look at the change in heights and see, since they're decreasing, we know that that average rate must be decreasing also. But here, even though these changes in height are decreasing, we didn't have the same change in time, and so this didn't really tell us too much. We had to go to the average rate of change to really see what was happening, that the average rate of change is actually increasing. That's why we see this graph here, a concave up graph, versus this one here. So here the average rate of change is decreasing, but over here it's increasing. But now both functions are decreasing functions. The output, the height in the second case, and the number of meters in this case, they're both decreasing, but they're decreasing in fundamentally different ways. One's decreasing at a decreasing rate, and the other, this one on the screen here, is decreasing at an increasing rate. You can see page 1 of the handout for more pictures and an explanation of that. Describe how the quantities number of minutes elapsed since you pulled the plug from the drain and the height of the water in centimeters in the tub change together as the water drains from the tub. Well, as the number of minutes elapsed increases, the height of the water decreases at an increasing rate. Is that right? Let's see. I think so. I'm just going to make that 2 sentences though. Furthermore, the rate of change of the height with respect to time is increasing.